So, for this very last class of the semester, there's still a bit of semester left. This for anyone who is at least contemplating doing the coding option for the final. So I would like to know if you're on the fence. Let me know pretty soon which option you're going to choose, because for those who take the oral one, then we need to schedule it. Now, for those who do the coding option, so I would like this everything turned in by Thursday, May 9th. So 2 weeks from this Thursday. Now, as far as rules, and there were some issues with this last semester, I really don't want to have it again. It's supposed to be your own independent effort. There are resources out there, feel free to use those, but the last semester I saw how this is where more than one student was doing the exact same wrong thing. I do notice, don't do it. Okay, but fortunately none of the people involved in that crowd last semester are here. Okay, now if we look at what's in Canvas. Okay, so I have a link to the coding option on the main page in Canvas. You can see, okay, we have a PDF of a handout I'm going to go through. I guess we shouldn't call them handouts anymore because we don't hand them out, but anyway. And then there's a starter code here, and we're gonna take a look at those two. But first, the documents. So as far as what you actually write, so first we have, so this is finite difference. This is section 13.2. Solving a linear 2-point boundary value problem. So it's going to be something in this form, where so then how do you specify what the problem is? You specify functions p of x, q of x, r of x. You specify the interval of the endpoints a and b, and you also specify the boundary values alpha and beta. So those are the input parameters to this function, as well as n. Now, n is the number of interior grid points. So, we know what solution is in the boundary. It's equal to alpha and beta, the left and right endpoints, respectively. So we're trying to compute y of x is at these equally spaced points in the interior of the interval AB. So the number of such interior points, which I always refer to in the notes as capital N. So the MATLAB variable lowercase n is the number of interior points. Now, P, Q, and R are function handles. You see me defining this now and then, like for example, I use something like P is @x, and then a formula. And you'll see an example of this. I'll still use the code that's going to test your functions. So the output to this F2 linear is first a vector of x values, which are just the all the grid points, including the boundary points. Very important; they must be included. So equally spaced points ranging from A to B, including A and B. So there should be whatever n is. This vector must consist of n plus 2 points. I'm going to make a note of that here. N plus 2 x values. Okay. And then the vector y, also consisting of n plus 2 values. So these are values of the approximate solution, approximation of y of x at these x values. So the first and last elements of the vector y will be boundary values alpha and beta. All values in between will be what your solution method produces. Okay. Now the script that I've included in the code, testcode.m. I'm going to talk more about it later. it's going to use your function to solve this boundary value problem. The exact solution is known, so it's going to check your function by calling your function to produce a solution and then compare to the exact solution evaluated at these same x values and get an error estimate. So it'll tell you what the error is. That error better be small or you messed up. And it'll do this at 100 grid points, 200 grid points. So not only can we see if your function is computing a solution with reasonable accuracy, but also checking the order of accuracy. The finite difference method that I presented in class is second order accurate. So if I double the number of grid points, the error should be reduced by a factor of roughly 4. So that's something that you'll be able to check. Now, if we look at what I posted for ftlinear.m, these come up. It drives me nuts when I try to open a file in Canvas and it does this. And it does it really often. I tried it on a different file and that one opened fine, but on this one, what I might have to do is download it. Okay, so here I have some comments to help you get started on ftlinear. When you're solving a linear BDP, all you're doing is you're solving system linear equations. So you have a matrix A and then a right-hand side vector R, and then you solve that using backslash to get the solution values Y. So really this is about setting up the matrix A and right-hand side vector R. So here you need the grid points for the interior. You need to evaluate your function handles P, Q, and R at these x values because you use the values of these coefficients in source term in setting up your matrix. There are formulas on this page of the text. Oops. Sorry about that. Page 524. Here we are. So here are the formulas for the matrix entries in terms of coefficients p of x and q of x. And then here are the formulas for the entries of the right-hand side vector R. Matrix A is tridiagonal. So once you set up those two items, then you just go ahead and solve the system. And that will give you a value of solution at the interior points. So then for the vector x, so we're assuming is a vector capital X has only the interior grid points that are defined here. And then I go ahead and do this for you where I add on boundary values. So A first and then B last. So you'll be doing the same thing for Y to add the boundary values in Y before your function exits. And then, as far as testing your code is concerned, see if this file opens in Canvas. Ah, there it is. Go figure. Oh, that's old. Okay, dang it. No, P, Q, and R instead of using this function inline, that's an old MATLAB command. Okay. I know I have a newer version of it somewhere. I will post it. I mean, inline will still work. I'll just give you a warning, like this is old. But once you have this code, do not mess with it. It's meant to make things easier for you. So you define P, Q, and R. Set your boundary values in X and in Y. And then this code right here tests using finite difference. So what it'll do is set number of grid points, and then it'll call your function with all the values that have been set to get the vectors X and Y. This is a formula for the exact solution of the boundary value problem. So what will happen is it will take the X values that your function returns and plug it into a formula for the exact solution. And then we'll call this function that I've included in what I posted, report results. And I'll show you what that one does. So do not mess with this function either. I mean, the only thing you should change in test code is this tests all the methods. If there are certain methods that you haven't implemented yet, or maybe there are certain methods you have working, so you don't want to test them anymore, but yeah, go ahead and comment out the appropriate parts of the code, but otherwise, don't touch it. Because once I have your code submitted, I'm going to test it. Okay, this is not working either. Dang it. All right. So what this does is, okay, how it's called. I'll go back to the test code. The only one is able to open Canvas for some reason. So I call report results using a text string that indicates what method it is, what function it is, the X values, Y values, the exact solution values, the number of grid points, and also the total time. That's just a curiosity item. Like here, I call the function tick before call empty linear, and then that starts the clock, and then I call talk when it's done, that stops the clock. So the variable total time, that's how long in seconds it took for your method to run. And it should not take very long in this case. So here, what's done is we get the error. That's very important. They're comparing your computer solution to the exact solution. Then we'll go ahead and plot both. So the product solution is plotted in blue circles and also a blue solid curve. The exact solution is plotted in red diamonds and a dashed curve. And those should pretty much be spot on for 100 grid points. If you see a noticeable discrepancy, then you messed up. And then all the annotation, it says saves the plot as a JPEG. And then gives some performance information. That's not really a big deal for its assignment. But you want to look at this error. You want to make sure that that's small. Like something in order to like 10 minus 5, 10 minus 7. I don't remember exactly, but it's pretty dang small. So, but certainly, I mean, when you see the plots, will be pretty much dead on. So that your practice work. Okay, so right now we've only talked about one method, but also how any of the methods are to be tested. So does anyone have any questions up to this point before I talk about other methods? Have I scared anyone off yet from doing this? Well, nothing's got to work harder. I'm kidding. Well, some people do it. But there's only 5 of you. Okay, but return to the document. Okay. There's only 2 problems on this. So this is the second one, and that's to solve a nonlinear 2-point boundary value problem. So now you've got the function handles for a function handle for f as a function of x, y, and y prime. And for Newton's method, also proves with respect to y and respect to y prime. So the first method to implement is the shooting method. So it uses Newton's method for solving the root finding problem that comes with the shooting method. You can use this formula for the initial guess. This is just the slope of a line that goes from between the two boundary points. And x and y equal to a and b, and y equal to alpha and beta. The parameters f, fy, and fyp are function handles for these functions. Which should be the end. Okay. Now, in the test code, here's how I set up a nonlinear boundary value problem. I need here's my boundary value problem: y double prime equals y cubed minus y prime. So I define the function handle this way. So this is all taken care of for you. Notice I use a dot exponentiation, dot multiply, because I have to allow for y and y prime to be vectors, and also x if it comes up. And then I take the partial derivative of this function with respect to y, and it gives me this. And then I also take the partial derivative of this function with respect to y prime, which just gives me minus y. And then I set my boundary values and go from there. And this is the exact solution that can work out as just 1 over 1 plus x. Okay. Now, and then the same unit mean for both all the error parameters and n number of interior grid points. We have an error tolerance that indicates when Newton's method should stop. So this is the convergence criterion that the difference the difference of a function value. This is what we want to be equal to 0. So instead of comparing successive iterates, we can check whether a function value is small enough, and then we stop. Same return value conventions. They return x, y values, vectors that include the boundary values. Also return the number of iterations of Newton's method that were needed. The Newton's method converges quadratically, so it should not be very many iterations. Now, take a look at what I posted for Newt. See if this all does in Canvas. Maybe it's only the first file. It does. That's the way it's looking. It's pretty stupid. I'll download this one too. Okay. So now notice there's two functions in here. Okay. So what's happening in this case is here we're applying Newton's method, and now what does Newton's method find the root of in this case? What it's doing is it's computing the solution of the initial value problem, where at x is equal to a, the solution is equal to alpha, and the derivative is equal to t, or tk. It goes ahead and computes the solution using the time-stepping method, like Euler's method, and then evaluates the computed solution at x equal b. We want that to be equal to beta. So in this function is where all the time stepping happens. So t and alpha are for the initial conditions, and then f is used for the fy and fyp defined as ODEs. Now this is for Newton's method. So if we look at the text, okay, so we're solving this system of ODEs that was covered in class, 4 ODEs in total. And these are the initial conditions. And how you're solving it is the approach given in 13.1.2. This right here. So basically what you're doing is you're implementing this. So in fact, and this part, choosing initial guess, that's given to you in the problem statement. So you covered there too. So this will carry out Newton's method with using forward Euler for time stepping. Now here it's just broken up in two. So really what you do is you inside your function newt f, because remember Newton's method is used to find a solution to the equation f of x equals 0. Newt f evaluates the f at t. So what you do is, so a part of highlighting all of this, setting the initial values given t and alpha, and also carrying out the Euler's method time stepping. That part of this part of highlighting what goes into newt f. The output of newt f is this: the value of your unknown y1 at the last grid point. So that's a part from Newton's method that you really care about for running Newton's method. But then if you look at the output, you want all values of y1 in the vector y, but it includes boundary values. That's because ultimately that will be the solution of our boundary value problem that we want to return from shoot newt. Now the other thing that's needed, yp, that is needed to be returned as output from all this because we need it here. Because remember, Newton's method is new x equals old x minus f value over f prime value. So this right here is the f prime value, the final output of the value of z1 at the last grid point. So that's returned in the second output. So the last element of capital Y and yp itself is a scalar. That's what it's used to carry out the Newton step. So questions about what to do for this function? No. Okay, so that's the shooting method for Newton's method. Part B is similar. It says you're changing shoot newt to use the secant method instead of Newton's method. So this is your main secant. Oh, this is so for Newton secant method. You need two initial values. This is how you get the second one. Now with if anything, this will be simpler in a way because you're only have solving the system of 2 ODEs instead of 4. So basically, you're going to be removing some things that you need for Newton because you don't need it for secant. The secant method does not require the derivative. Otherwise, the way things are set up is exactly the same. But notice you have fewer parameters because you only need f. You don't need fy. You don't need fyp. I'll just go ahead and download this and try to help Canvas. Okay, there's not much to say here. So again, it's stripped down Newton's method. Okay. All right. The last method to implement is FT Newton. So this is a finite difference But for nonlinear problems, that means now you're using Newton's method to solve a system of equations. Whereas with shooting method, you're using Newton's method to solve a scalar equation for the slope t. Now, so in this case, your Newton's method is a function of x. So here we use our initial guess for Newton's method. This will be a linear function that connects the boundary points a alpha and b beta. And okay. So I'm going to go to the code. All right. So what you're doing is Newton's method for solving a system of equations. Now that's actually described in chapter 11, which I covered briefly before getting into ODEs. I have the algorithm here for you. Okay, so this is Newton's method for a system of equations. The initial guess that's prescribed in the problem statement. So then you're so the function type you're given is value of your function. You solve a system of equations following a Jacobian. Minus the function handles your right hand values your right hand side, and then this is your main Newton step until convergence. So what you really need is, okay, what is f? What is the Jacobian? Okay, now, so really, FT Newton had these two helper functions, my f and my j for Jacobian. So your Newton's method iteration will call this function to get an f value, and the formulas for f are given. I'll navigate to those. Text. Okay. I should correct what's in the code here. These are the formulas for f of y. The function trying to find a multivariable root of. So equation 13. Yes, that's really what was formula given. And then for the Jacobian, we have these formulas for the from the integers of Jacobian, which is a tridiagonal matrix. So you'll be coding these up. So that's equation 13, 14. Why don't we say page 528? 526. Hold on. I need to reconcile this because it'll drive me nuts. Okay, these are formulas for Jacobian for a specific case. Okay. Okay, for my f, as I use a formula code for f1 from example 13.2.3. So I gave you the formulas for f back here, equation 13.13, but that's actually, the code for that is actually given to you in this example 13.2.3. Okay, so I'll try to list that. Here it is. So the only difference is I have alpha and beta as separate arguments. Okay. So Here, it's assumed that x and y coming in include the boundary values, and then for certain variables, we take only the interior ones. So that's why this works very smoothly. But in this case, here, y is only the interior values, and then we have the boundary values separate. So the code will be a little different. Or what you can do is you can take alpha and beta, lump them into with y, and then the code will be exactly the same. So it's up to you. And then similar code you would need to write for Jacobian part. Okay. So what you'll do inside the actual FT Newton function is you're implementing this algorithm, and whenever you need to call f, you'll call within the algorithm you need to call my f. When you need the Jacobian matrix within this algorithm, you'll call my j to get the matrix, and then you use solve system js is equal to minus f. And then keep iterating until convergence, and then you'll have your solution in however many iterations. So there's a lot of breadcrumbs given here. Okay, here are the convergence criterion, just checking whether the difference in successive iterates is left, and the tolerance is passing. And then the script test code is set up to solve this boundary value problem using various methods. So shooting method of Newton, shooting method of secant, and also finite difference. Okay, and how does the accuracy improve as the number of inputs increases? Finite difference should be second order accurate. Do we actually get that? And that's the end. I'll say surprised I got that much time. Okay. So do we have any questions about any aspect of this assignment? Okay. How many of y'all think you're going to do it? Okay, one.
I doubt it.
What?
I doubt it.
Okay.
Probably not.
Okay. Anyone else? Or are y'all still on the best? Okay. I'm including our 2 online people. Everyone inside the room is spoken. Maybe not even paying attention. Okay. Well, if you have decided that you're going to do the oral, then please let me know sooner rather than later for scheduling it. We've covered everything, so that anything can be included. Okay, I guess that's it then.
Will the oral test be during the week of finals? Like, can we schedule it during that week, or does it need to be the week before?
I don't really care when. I mean, I'm trying to wrap up everything by the 9th, no matter what's done. So that's really your preference if you want to schedule during finals week, or if you want to have it earlier.
Okay, thank you.
Okay. And I guess a good argument can be either way for sooner or later. All right, any other questions about anything? Now it comes to the very end of the semester. Well, at least this class, that's not the end, the rest, but, well, it's been real.